Hi there, I'm Shaul Almagor, and I'm going to tell you all about parametrized universality problems for one-counter nets. This is a joint work with Boker, Piotr Hofman, and Patrick Totzke. Let's start with the model we study, namely one-counter nets. We start with a finite state machine, so we have some states Q, some of which are accepting, and non-deterministic transitions between them, labeled by some alphabet sigma. And we obtain from it a one-counter net, or OCN for short, by labeling every transition with an integer weight. Semantically, we equip the state machine with an integer counter that is not allowed to go below 0. For example, suppose we are given the word A, B, B, C, and suppose we start the counter with the initial value 3. Then, a possible run on it progresses like so, ending up in the accepting state with weight 4, and the counter never becomes negative. However, the run that proceeds to the lower branch cannot continue to read A, B, B, since it would cause the counter value to become negative. We say that a word W is accepted by an OCN with initial counter S0 if there is some run on the word W, starting with counter value S0, that ends in an accepting state. So in the example, W is accepted with counter value 3, but observe that it is not accepted with counter value 2 or lower. OCNs are also known as one-dimensional vector addition systems with states, as Petri nets with exactly one unbounded place, as Minsky machines with only one counter and no zero tests, and as push-down automata with a single-letter stack alphabet, so they are well studied in many contexts. Now, given an OCN and an initial counter value S0, we define LS0 to be the language of words that are accepted with the initial counter value is S0. Then, the vanilla universality problem is to decide, given an OCN and S0, whether LS0 is sigma star, that is, whether every word is accepted from the initial counter value S0. This is a fairly well-known problem. We'll elaborate a bit more about it in the next slide. In this work, we also consider a parametrized version of it, called initial value universality. There, we're given an OCN, and we need to decide whether there exists some initial counter value for which the language is sigma star. We also consider a bounded version of universality, where we ask, given an OCN and an initial counter value S0, whether there exists a bound B, such that every word is accepted with initial counter S0 by a run whose counter values stay below B. That is, we define LS0 bounded by B to be the language of words that are accepted with initial counter value S0 with a run whose counter value stays below B. Then, the bounded universality problem asks, given an OCN and an initial counter value S0, whether there exists a bound B such that LS0 bounded by B is sigma star. Our results are summarized in this big table. We separate the results based on whether the weights are encoded in unary or binary. For each of the three universality variants, we further separate based on whether the automata are deterministic, unambiguous, or generally non-deterministic, and on whether the alphabet is singleton or not. So the picture in this table is fairly fine-grained. You can see that we have quite a large range of complexities here, with the most restricted fragments, deterministic OCNs over a Singleton alphabet, being in L for unary encoding and in NC2 for binary encoding, and the most general cases going up to Ackermann and to undecidability. We won't go through the whole thing, of course, and the rest of the talk will focus on the undecidability results and on the case of a Singleton alphabet. Before moving on, as you can see from the table, the vanilla universality problem has already been studied here and here, showing that the problem is Ackermann for a general non-deterministic OCN and easier for unambiguous OCNs. We start by showing the undecidability of initial value universality. This will be done using a reduction from the halting problem for two-counter machines. A two-counter machine is a program consisting of lines L1 to Lk, where in each line we have a command that either increases or decreases one of two counters x and y, or performs a zero test, or unconditionally jumps to some line, or halts. For example, the program here starts by increasing x, then repeats a loop that decreases x by 1 and increases y by 2 until x becomes 0, and then halts. The problem of deciding whether a two-counter machine halts is undecidable, and we reduce it to the initial value universality problem. Specifically, given a two-counter machine with lines L1 to Lk, we construct an OCN A that is initially universal if and only if M halts. Intuitively, A reads descriptions of supposed runs of M, which may or may not be actual legal runs. For this description, we separate between the results of zero tests, so the alphabet of the OCN A consists of the commands increase x or y, decrease x or y, a zero result of zero tests, a non-zero result of a zero test, go to, halt, and the new symbol sharp. So the OCN we build reads words that consist of segments of commands separated by sharps. These segments supposedly follow the runs of the counter machine. For example, the legal run of the program here can be written as the segment increase x is greater than 0 so go to L3, decrease x, increase y, go to L2, x is 0 so go to L7, halt. But of course there can be other segments that don't represent the run or represent prefixes of it. The idea now is that A accepts a word if it satisfies any of the following conditions. Either the word has a segment that is shorter than the halting run of A, for example the segment sharp, increase x is greater than 0 so go to L3, sharp, or the word has a segment that violates the control structure of A, which we call a non-counting cheat. For example, the segment sharp, increase x is greater than 0 so go to L3, increase x sharp, which is illegal since we're expecting decrease x in the last step. Or all of the segments violate the counter tests, which we call counting cheats. For example, the segment sharp, increase x is 0 so go to L7, halt, sharp, which is illegal since the segment claims that x is 0 when it is not. Okay, let's delve into the construction. We start in the state Q0, where we can read anything up to the first sharp without changing the counter value. Think of the initial counter value as some number n. Remember, we're dealing with the initial value universality problem, so we're asking whether there exists some initial counter value that makes the language universal, so it makes sense to think of it as some unknown value. Alright, once we see a sharp in Q0, we non-deterministically guess which type of violation is going to occur. We'll go over these one by one. The first type of violation is having a segment that is shorter than the accepting run. To handle this, we have a transition on sharp to state Q1 here, in which we can read any command while decreasing the counter. Thus, we can stay in Q1 only for so long, until the initial counter runs out. If, during this short stay, we see a sharp, we go on to the accepting sync. This means that if there is a short segment, the word will be accepted. The next violation we take care of is a non-counting cheat, that is, seeing a command that is structurally illegal. To handle this, we have again an undeterministic branch on sharp from Q0, taking us to the command checker gadget. The command checker simply follows the commands of the counter machine, having a state for each line of the counter machine. So when the expected command is an increase, decrease, or go to, the transition is clear. When the command is a zero test, then the command checker allows both possible go to branches, because it cannot keep track of the counter value. This is why the command checker only works for structural violations. If a violation is detected in the command checker, then we again go to the accepting sync. So the command checker plugs in here, and we move on to the next violation, which is a counting cheat. We actually separate these to zero cheats and positive cheats. A zero cheat for the counter x means that at some point we saw the command x equals 0 so go to Li, but the actual counter value for x was positive, not 0. To handle this, we add a transition on sharp from Q0 to a new state Q2, where we simulate the counter value for x. That is, if we see the command increase x, then we increase the counter, and if we see the command decrease x, then we decrease it. All other commands do not change the counter value. If we see the command x equals 0 so go to Li, then we have two options. Either stay in Q2, so we guess that the actual cheat comes later, or we guess that the cheat is now and go back to Q0, but the counter decreases by 1. The idea here is that if there indeed was a counting cheat, then x was positive, meaning that we saw more increments than decrements, so the last transition with cost -1 still puts us back in Q0 with at least the counter value we started with, so we can proceed with the run. If, however, there was no cheat, we might still get back to Q0, but we can only do this for so many times before the counter decreases to 0. This means that if the counter machine does not halt, then for every initial counter value, a word whose segments represent legal run prefixes is not accepted in this component if it has enough segments. We also have a state Q3 that performs the same violation check for the counter y. Finally, we have states that perform positive cheats. The idea is somewhat similar to the zero cheats, where we actually keep track of the negated counter value. We won't go into the details because we don't want to spoil the entire paper. Using this construction, we show that initial value universality is undecidable. In fact, using some variations on this construction, we can also show that bounded universality is undecidable. Back to the big table. Undecidability applies both to unary and binary encodings. We now move on to one of the fragments of the problem, the case of unary alphabet. For this case, we will look at the vanilla universality problem. When the alphabet consists of a single letter, the OCN is sort of a weighted graph, with accepting states. Now, for NFAs over a unary alphabet, the universality problem is CONP hard. This trivially carries over to OCNs. So we're aiming at an upper bound by means of bounding the length of a non-accepted witness word. The key ideas for bounding this length are good cycles, which can be moved around, and then using some bounds on DFAs. We'll start by looking at cycles that can be plugged and shifted around the run. Consider some long run. In order for the counter value to stay positive, the run must have non-negative cycles. We ask ourselves which cycles can be moved around the run. Some non-negative cycles, before ending up as non-negative, do have a negative prefix. We can't move these cycles because other parts of the run might not have sufficiently large counter value to take the negative prefix. However, cycles that start in their nadir, their minimal counter phase, can be moved around freely, as they can even be taken with counter value 0. We call these good cycles, and states that admit good cycles are good states. Now, consider a long run that goes through a good state. By some careful rearranging, we can convert the run to a run of the same length, and hence on the same word since the alphabet is unary, that has the following form. It starts with some relatively short prefix mu1, then a good cycle gamma, taken t times, and then a short suffix mu2. The idea here is that if there are enough cycles of various lengths, we can replace them with repetitions of a good cycle on R. Using this, we can prove the following. For every good state R, we can construct a DFA of polynomial size that accepts every word that is accepted by the OCN with a run that goes through R. Note that polynomial here means polynomial in the description of the OCN, so if the weights are encoded in binary, this can still be pretty big. We use the DFAs for good states to prove the following. There exists a polynomial bound B, again polynomial in the description of the transitions and the number of states, such that the language of the OCN is not universal if and only if it does not accept the word of length n, such that either n is at most b, or n is between b to the q and 2b to the q. The idea behind this is that DFAs over a unary alphabet are lasso-shaped, so either a short word is not accepted by all of the DFAs in their finite prefix, or a long word is not accepted by all the DFAs in their loop part, and we obtain the bound by reasoning about the loop length of the DFAs. This allows us to take a guess and check approach, but unfortunately the length of the witness can be exponential, even in the unary case. Nonetheless, we're able to prove that for unary encoding we can check the exponential witness in polynomial time, giving us CONP completeness. In the binary case, however, things are more elaborate, and we're only able to prove membership in the second level of the polynomial hierarchy, namely in CONP to the NP. Let's go back to the big table. Note that the approach we took regarded vanilla universality. As for Singleton Alphabet and unary encoding, universality is CONP complete. And for binary encoding, universality is in CONP to the NP with a lower bound of CONP hardness. Now, for initial value universality, it is not hard to adapt the same method of cycle shifting. In fact, it makes things somewhat easier, since we can kind of ignore the short words as they don't give us much trouble with large enough counter values. So we actually get membership in CONP for initial value universality for both unary and binary encodings. For bounded universality, we have to put in some more work. Specifically, good cycles are not enough, since we must keep the counter from going too high. But we can tweak the definition of good cycles, and a similar scheme works. So we're able to obtain similar complexity results. CONP completeness for unary encoding, and CONP to the NP for binary encoding. Okay, some last remarks before I go away. OCNs are a very useful modeling tool, which can be thought of as a restriction of many stronger models, VAS, PDAs, Petri nets, counter machines. Unfortunately, many problems remain undecidable or difficult even for OCNs. But if we restrict OCNs to fragments, it may significantly reduce the complexity of certain problems. To handle these restrictions, we might need to come up with new algorithms, so it's not like the same bad algorithms suddenly perform well for fragments. Some useful tools to keep in mind if you're working with OCNs. For undecidability, the technique of guessing violations is often useful and can be implemented with relatively simple gadgets. For obtaining short witnesses, or at least witnesses with a short description, it is often useful to bring runs into some canonical form. This usually involves some painful cycle analysis, but turns out to be worth it. Various NC bounds for arithmetic are used when the encoding becomes the dominant complexity part. For example, when the OCNs are deterministic but encoded in binary. And when the dominant part is a structure, the algorithms for finite automata often become useful. Thank you for listening.